Motion of a body on a smooth inclined surface. Suppose in the figure, the inclined line represents a smooth inclined surface which is at an angle theta with the horizontal. That rectangle on the inclined surface represents a block. Its weight mg acts vertically downward direction. Then a component of this weight mg cos theta acts normal to the inclined surface. Hence, the normal reaction n will be equal to mg cos theta. Another component mg sin theta acts down the inclined surface and pulls the block downwards. When the surface is smooth, this force mg sin theta creates acceleration. This creates acceleration. So the acceleration created is equal to mg sin theta by m, force by mass. Mg sin theta creates acceleration. Hence acceleration created is equal to force by mass, mg sin theta by m. So that is g sin theta. The acceleration on the inclined surface is g sin theta down the inclined surface and along parallel to the inclined surface. If the block is placed at the top of the inclined surface, which is at a height small h, then because of this acceleration, it slides down along the inclined surface. The length of this inclined surface is say L. Its initial velocity is 0, so its acceleration is g sin theta. Let us suppose the velocity at the bottom of the inclined surface is v. Let us calculate this velocity v. U is 0, s is L, v is how much, and a is equal to g sin theta. By selecting the equation b square minus u square is equal to 2as and substituting these values, we will get v square is equal to 2 into g sin theta into L, because u is 0. V square is 2gl sin theta, or v is equal to square root of 2gl sin theta. V is equal to square root of 2gl sin theta. The height of the inclined surface h is equal to L sin theta. From geometry, h is equal to L sin theta. Hence, v is equal to square root of 2gh. We get the same relation for a vertically falling body, but we have to remember that the direction of velocity on the inclined surface will be along the inclined surface and down the inclined surface. It is not vertical. The direction is different. Time of reaching the bottom of inclined surface. Let us suppose the time taken to reach the bottom of the inclined surface is say t. Then we can find the relation for t using the following parameters. U is 0, a is equal to g sin theta, displacement s is equal to L, and t is how much. U is equal to 0, a is equal to g sin theta, s is equal to L, and t is how much. Use the relation s is equal to ut plus half at square. So L is equal to ut becomes 0. So half into g sin theta into t square. L is equal to half g sin theta into t square, from which t is equal to square root of 2L by g sin theta. T is equal to square root of 2L by g sin theta. With this relation, we can find the time taken by the body to slide down the smooth inclined surface. If a body is pushed up the inclined surface with a velocity u and it reaches a maximum distance x on the inclined surface, we can find the relation for x. Here u is equal to u. The upward direction is taken as positive. Along the inclined surface, up the inclined surface is taken as positive. So acceleration a is equal to minus g sin theta. Displacement s is equal to x. When it reaches the maximum distance, the final velocity v is equal to 0. V is equal to 0. Now take the values. U is equal to u, v is 0, a is minus g sin theta, s is equal to x. Use the relation v square minus u square is equal to 2as. Then we will get 0 square minus u square is equal to 2 into minus g sin theta into x. Therefore, u square is equal to 2gx sin theta. So x is equal to u square by 2g sin theta. X is equal to u square by 2g sin theta. This is the relation for reaching the maximum distance along the inclined surface, smooth inclined surface. Time of reaching the top of the inclined surface. Here u is equal to u, a is equal to minus g sin theta, and v is equal to 0. To reach the maximum distance on the inclined surface, if the time taken is t, let us find a relation for t. U is equal to u, a is equal to minus g sin theta, v is 0, t is how much? Take v is equal to u plus at. So 0 is equal to u minus g sin theta into t. U minus g sin theta into t, or g sin theta into t is equal to u. Therefore, t is equal to u by g sin theta. T is equal to u by g sin theta. With this relation, we can calculate the time taken to reach the maximum distance on the inclined surface, smooth inclined surface. Now let us proceed to find the motion on rough inclined surface, to study the motion on rough inclined surface. When the block is placed on a rough inclined surface, then its component mg cos theta acts normal to the inclined surface and mg sin theta acts down the inclined surface. Because of mg sin theta, the block is pulled down, it is moved down. Whenever the block begins to slide down, a frictional force acts up the inclined surface, that is Fs. This is the frictional force in the static condition. We know that at a particular angle, as the angle of inclination increases, mg sin theta increases. So Fs will also increase. Fs will also increase because with the increase in theta angle, the component mg sin theta will also increase. So the static frictional force increases with inclination. At a particular angle of inclination, say alpha, this block is just about to slide down. So that is the maximum static frictional force. It is the maximum static frictional force. So Fs is equal to mu s into mg cos alpha. Alpha is the angle at which the block is set to move. Then the component becomes mg cos alpha and normal reaction becomes mg cos alpha and static frictional force becomes equal to mu s mg cos alpha. This will be equal to mg sin alpha, which pulls the block down the inclined surface. So mg sin alpha is equal to mu s mg cos alpha, from which we get mu s is equal to mg sin alpha by mg cos alpha, that is equal to tan alpha. So if mu s is the coefficient of static friction, by using the relation mu s is equal to tan alpha, we can find the angle. This angle is known as angle of repose. If the inclined surface is making an angle less than this angle, then the block will not slide down. Motion of the block down the inclined surface. Let us study the motion which depends on inclination. As theta is increased at a particular angle, it begins to slide down. I have shown here three stages. Theta is equal to alpha, theta is less than alpha, theta greater than alpha. Alpha is angle of repose. So when the inclined surface is making an angle theta is equal to alpha, then the block placed on the inclined surface is set to slide down. If the angle is less than alpha, then the block will never slide down. Under its own weight, it will not slide down. But if the angle theta is greater than alpha, then the block slides down along the inclined surface. In such a case, the maximum static frictional force will be less than mg sin theta. So if theta is less than alpha, then Fs maximum is greater than mg sin theta. If theta is equal to alpha, Fs maximum is equal to mg sin theta. If theta is greater than alpha, then Fs maximum is less than mg sin theta. Hence, the body slides down the inclined surface with some acceleration. Acceleration down the rough incline. Suppose a block is placed on a rough inclined surface. Then the weight of the block mg acts vertically downwards. The component mg cos theta acts normal to the inclined surface, and thereby a normal reaction n is created, which is equal to mg cos theta. Then the second component mg sin theta acts down the inclined surface and pulls the block down the inclined surface. Then the frictional force sets in, which opposes the motion and it acts along and up the inclined surface. So mg sin theta is down the inclined surface and Fs is up the inclined surface. The resultant force Fr is equal to mg sin theta minus Fs. Due to this force, resultant force, the block moves down. When the block is in motion, then the frictional force is kinetic frictional force. So it becomes Fk. Fk is equal to mu k mg cos theta. Fk is equal to mu k mg cos theta. So when it is coming down, if A is the acceleration, of the block, then Fr is equal to ma. Fr is equal to ma. Hence, ma is equal to mg sin theta minus mu k mg cos theta. ma is equal to mg sin theta minus mu k mg cos theta. From this, acceleration A is equal to g sin theta minus mu kg cos theta. G sin theta minus mu kg cos theta, or g into sin theta minus mu k cos theta. G into sin theta minus mu k cos theta. This is the relation for acceleration down the rough inclined surface. Acceleration in different situations. Acceleration in different situations. We have seen the relation for acceleration on rough inclined surface is obtained from the relation ma is equal to mg sin theta minus mu k mg cos theta, from which acceleration is g sin theta minus mu k g cos theta. Let us recollect the situations. Consider a freely falling body. Its acceleration is equal to g. This is in the vertically downward direction. On a smooth inclined surface, the acceleration is g sin theta. It is down the inclined surface and the acceleration is g sin theta on smooth inclined surface. When we consider a rough inclined surface, the acceleration is g sin theta minus mu kg cos theta. So, A is equal to g, freely falling body, A is equal to g sin theta on smooth inclined surface, A is equal to g into sin theta minus mu k cos theta on rough inclined surface. Relation for velocity at the bottom of rough inclined surface. When the body slides down the rough inclined surface, let us calculate the velocity attained when it comes to the bottom. For this, let us consider the body is freely dropped. So, u is equal to 0, the distance travelled s is equal to L, length of the inclined surface, and the acceleration down the rough inclined surface is g sin theta minus mu kg cos theta. Let us find the final velocity v. For this purpose, let us use the relation v square minus u square is equal to 2as. Substituting v square minus 0 square is equal to 2 into g into sin theta minus mu kg cos theta into L. 2 into a is g sin theta minus mu kg cos theta and s is L. So from this we get v is equal to square root of 2gl into sin theta minus mu k cos theta. V is equal to square root of 2gl into sin theta minus mu k cos theta. V is equal to square root of 2gl into sin theta minus mu k cos theta. Time of reaching the bottom. Time taken to reach the bottom of the inclined surface. To obtain a relation for time, consider the initial velocity u is equal to 0, the distance travelled s is equal to L, length of the inclined surface. The acceleration on rough inclined surface is g sin theta minus mu kg cos theta. Let us find time t. From s is equal to ut plus half at square, we get L is equal to 0 plus half into g sin theta minus mu kg cos theta into t square. L is equal to 0 plus half into g sin theta minus mu kg cos theta into t square. From this we will get t is equal to square root of 2L by g into sin theta minus mu k cos theta. T is equal to square root of 2L by g into sin theta minus mu k cos theta. This is the relation for time. Motion up the rough inclined surface. The block can move up the inclined surface provided a force F acts on this block along and up the inclined surface. Let us suppose the force is along and up the inclined surface. This force is say capital F. When the block moves up the inclined surface, then the frictional force acts downwards along and down the inclined surface. So the minimum force required to move the block up the inclined surface is mg sin theta on smooth inclined surface, because there will be no friction. There will be no friction on smooth inclined surface. So F minimum is equal to mg sin theta. On rough inclined surface, it is mg sin theta plus mu mg cos theta. Here mu is mu k. F minimum force required is mg sin theta plus mu k mg cos theta. This is the minimum force required on a rough inclined surface. If the force F is greater than this minimum force, then the resultant force is F minus of mg sin theta plus mu mg cos theta. This is the resultant force. F minus of mg sin theta plus mu mg cos theta. This resultant force by mass gives the acceleration. So acceleration is equal to F minus of mg sin theta plus mu mg cos theta whole divided by m. This gives the acceleration up the inclined surface when the block is pulled up with a force F.